In 323, and from the Seleucid era, which started after, we have an explosion of astronomical texts, so which are the subject of our discussion today. Let me first describe the mathematics of the astronomical text dogmatically, and then answer the question how we know this. So I start with mathematics. Mathematics is quite simple. And conjecturally, this mathematical theory comes from the previous Achaemenid era, so roughly 500 years before Christ. So the main object for us is the so-called zigzag function. Zigzag function. Zigzag function is a piecewise linear function.
Я ничего абсолютно не вижу.
Zigzag function, like this. Zigzag function. So this is a piecewise linear function whose slopes are the increasing slope is minus the decreasing slope, like this. So this is the zigzag function. So the derivative of a zigzag function is a piecewise constant function. The antiderivative, the antiderivative we will consider for the purposes of this talk, antiderivative and second antiderivative, and not just of zigzag function, but also of some more general piecewise linear functions. But the key building block is this zigzag function. So clearly, this function has mean value, which is the half between maximum and minimum. And then, obviously, there are also oscillations between mean value. And also, mean value can be approximated also if I don't know the zigzag function very well, but I know it for a very long time. I can approximate mean value, in fact, not badly. And then, if I want, I can have correction terms in terms of another zigzag function. Of bigger period. Okay, so which quantity, what was the problem that Babylonian astronomers solved? So the problem, there were several key problems. So first of all, there was key problem of eclipses. So when the sun is eclipsed, it's not possible to start a war, for example. The soldiers won't do it. There are famous stories, Herodotus mentions one, and well, the Lay of Prince Sigurd mentions another, so it's just not possible. Then, the calendar, the Babylonian calendar was a lunar calendar. In fact, the key god was the moon, the sun was the secondary god. The day started at sunset, yes. So, and the calendar was lunar calendar, but of course, clearly for agriculture, you also need solar calendar, and then there are delicate intercalations between solar and lunar calendar. So precisely, this is what we want to measure as well. Also, clearly, length of daylight is an important parameter. Precisely for this length of daylight, the third antiderivative of piecewise constant function was used, length of daylight. So how did Babylonians measure time? This is a very subtle question which I will not go in detail. I will answer just very briefly by water clocks. So precisely one wants to measure the appearance of the moon. But there is the moon and the sun, so there are two bodies, they move at very different velocities. So if two bodies move at very different velocities, then the position of the point of intersection of this CZG depends mainly on the slow body, while the time depends mainly on the faster body. So then there are all these very subtle computations. Again, I will mention a few details a little bit later. Very subtle computations based on piecewise linear functions and mainly zigzag functions, and piecewise constant functions, and successive antiderivatives of these functions up to third order. Up to third order. Okay, so this description of mathematics in Babylon 500 years before Christ raises the question, how do we know this? How do we know this? And here I finish the strictly mathematical part of the talk. Are there any questions this far? So, and I go into the history. Our history starts in the 17th century with an Italian composer, Pietro della Valle. He was a Roman composer. He had an unfortunate love affair, and instead of suicide, he decided to go to the Holy Land. So he went from Venice to Constantinople, then from Constantinople to Alexandria, then from Alexandria through Sinai, he traveled to Jerusalem, and then he continued. So far, this is what you did if you wanted to visit the Holy Land. But then he traveled on to Damascus and to Baghdad. And from Baghdad, it's not very far, to the ruins of Babylon. He described the ruins of Babylon, and he brought bricks. He brought bricks. In fact, apparently not from Babylon, from Nineveh, but okay. But the important part is that he brought bricks with inscriptions. So then begins a long saga, which I will really narrate very, very briefly, of reading the cuneiform. Reading the cuneiform. So how to read the cuneiform? It's, again, it's a long, convoluted story, which I make very brief. So there was famous Danish expeditions, so-called Danish-Arabian journeys. There were 6 researchers who went there, and 5 died, and the only one who survived was a mathematician. So Carsten Niebuhr, and he copied very carefully some inscriptions from Persepolis, and from these careful copies it was possible to reconstruct very slowly, very gradually, and moving in inverse time, it was possible to gradually reconstruct the cuneiform script. So first, it's, again, in very broad outline, it's similar to reconstruction of the hieroglyphics. The difference is that it's much more complicated. So one started from later languages of which one had some idea, and also one had the idea of the Aramaic alphabet, and then one moved back in time. So in one of the discoveries that one made along the way, there were many scientists, I will not be able to mention all of them. One of the discoveries that were made along the way is that the Akkadian language, which is Semitic language, and roots in Semitic, again, in very first approximation, roots in all Semitic languages, they're the same. I mean, it's not true, but the first approximation it is. But then they discovered that there were some roots which were completely not Semitic. So Semitic, everybody knows, Semitic roots mainly have 3 consonants. But they discovered a lot of one-syllable words. So that's how they discovered Sumerian language and Sumerian peoples. It was purely theoretical discovery, Sumerian language, Sumerian people. Okay, so the reading of cuneiform and the discovery of Sumerian, Babylonian and earlier Sumerian literature brought a very uncomfortable question of possible Babylonian influence on the Bible, or even Sumerian influence on the Bible. So there is a Sumerian prototype of the Great Flood, there is a Sumerian prototype of creation of the world, of the first book of Genesis, and so on, and it was a politically charged debate. The Jesuits realized that if they wanted to take part in this debate, they needed to build up the competence to read the cuneiform. And so the Jesuits became some of the leading Assyriologists of the day, and Father Strassmaier started to read tablets. There were huge amounts of tablets, mainly in the British Museum, so the British Museum was buying that. And at some point he discovered tablets with huge amount of numbers. The tablets with numbers. Since the tablets also contained zodiac signs, he understood that these were astronomical tablets. But he was unable to decipher them, and in fact it's very clear why he was unable, as the deciphering took somewhat less than 100 years after he made this discovery. So he invited 2 other Jesuit priests, so there is Strassmaier, then there was Epping, and there was Kugler. 3.
Черным, да?
Черным.
Ну ладно, хорошо.
Kugler and Kugler, Franz Xaver Kugler. So Strassmaier discovered and Epping and especially Kugler deciphered. It's very complicated. Tablets are preserved partially, so one needed to recompose the tablets. So also tablets, it's just some 18 columns of numbers. It was very difficult to understand what the columns actually meant. So this took a very long time, and again effort of several teams of researchers. And in the modern time, there is especially the fundamental work of Otto Neugebauer, the author of Zentralblatt and Mathematical Reviews, so Otto Neugebauer, and by the way, also of Van der Waal. And also many more names, many other researchers. So it has to be emphasized and re-emphasized. So first of all, while we do have many tablets, over 1,000, they come from just two sources, from Babylon proper and from Uruk. They come, as I mentioned, mainly from the Seleucid era. So roughly speaking, between 300 and the birth of Christ. 300 before Christ, so the death of Alexander and the birth of Christ. So we have a lot of information, but sharply localized in time and in space. Since tablets are being discovered every day, and among the tablets which are the property, say, of the British Museum, over 100,000 of them, many, only a relatively small proportion is published, and not clearly all of them are even copied, deciphered. So all the recovery, it must be emphasized, it is theoretical, and it is obviously conjectural. So the numbers of the tablets are seen to match some astronomical data, as we shall see, very subtle. So it is quite possible, and Neugebauer especially, so Neugebauer is a mathematician, he studied in Göttingen, and just then he switched to history of mathematics, and just it's very clear, he absolutely emphasizes that this is not rigorous proof. So there are just some numbers. Also, there are not only numbers. There are numbers, but also instruction tablets. Tablets for making the tablets. Tablets for making the tables of numbers. So it's a little bit more than numbers. But still there is a huge work of reconstruction, and clearly tomorrow one might discover a new tablet, and then there will be important corrections to this theory. So this theory is, it must be emphasized and re-emphasized, is theoretically recovered from tables of numbers and some difficult to understand instructions about making tables of numbers. So it is largely work of reconstruction by, again, Kugler and especially Neugebauer and many other people, Van der Waal and many other people. It is exposed. So Neugebauer wrote two fundamental monographs. One is called Mathematical Cuneiform Text, in fact in German, Mathematische Culture Text. He was still in Germany at the time. Then he moved from Germany to the United States in the 1930s. And he also moved from Babylonian mathematics to Babylonian astronomy. And he wrote, again, he published this fundamental work, Astronomical Cuneiform Text. It's published, one can check it. It's really big amount of data, but also, I emphasize this, very important work of reconstruction. Very important work of reconstruction. So, and then many other, Van der Waal and many other colleagues also took part in this reconstruction project. So, specifically, just to give an example, I'm now quoting a famous book of Van der Waal, Science Awakening. Science Awakening is translated into Russian, by the way, it's in two parts, mathematics and astronomy. So this is the astronomical part. So what are reconstructions of tables? And I want also to make it clear, so since we don't want to go on until midnight, I'm really condensating a lot, and specifically I'm not even discussing the measurement units. So Babylonians had specific measurement units. One of them are degrees, the one we use today. Degrees come from Babylon, but also they had their own measurement units, barleycorn, large hours. So latitude was measured in one kind of unit, but longitude was measured in another kind of unit. I'm leaving all this, I'm putting all this under the carpet. So I'm giving a very, how shall I say, I'm giving an approximate picture. In fact, Babylonians themselves were masters of approximation. They were very good at approximate calculation. I'm giving approximate picture, and for more precise exposition, I refer precisely to the book of Otto and to fundamental work of Neugebauer. Okay, so just to give you an idea, so what they give? Well, obviously they put the year. It has to be emphasized that the date one reads in history books, the beginning of the Seleucid era, for example, when was that? How do we know that? We know this from astronomical tablets of Strassmaier. When the Seleucids were overtaken by the Parthians? How do we know this? Because they were dating documents by Seleucid era, and then they were dating documents by Parthian era. How do we know when the transition happened? We know this from documents of Strassmaier, because we have a very good idea about the degree of precision of Babylonian observations. Precision was not very great, but importantly, it was over a very long time. And so the pattern allows very precise dating. Okay, so there is the year. Then, of course, there was this, well, Babylonians observed that the period, what is a long period, well, clearly months does not contain, if months is defined as time between a new moon and new moon, then months contains not integer number of days. It's integer and something. So year contains not integer number of months and not integer number of days. And so they had this practical period that they called sagas of 2023 months. So, and one of the columns, just to give you an idea, one of the columns is the fraction part of the day of the difference of new moon in this month and next Sagas period. So 223 months from this. So this fraction part, well, the integer number of days is constant. The fraction part is the thing they record. So this is famous column F. Then obviously longitude of the moon in degrees, duration of daylight in large hours. These are not 4 times the usual hour. By the way, also, Neugebauer also emphasizes this a lot. It's a mathematical theory, and Babylonians, the aim of Babylonians was to have simple practical theory, good for practice. For example, to give a specific example, they, for computation of ratio of longest day to shortest day, they had ansatz 3:2. It's good. So considering that Babylonians did computations up to seven sexagesimal digits, so it's clearly they were. It's reasonable to think that they were aware of the approximate character of this formula. That longest day to shortest day is 3:2.
Longest day in the year?
Yes, it is. Longest day in the year to shortest day in the year, 3:2. So clearly it is natural to conjecture that they understood the approximate nature of this. But it was good enough for practical purposes with which they were concerned, and so they took this. When they need it, they do computation until 7 sexagesimal digits. When they don't need this, they do simple practical ansatz like this, for example, 3:2.
And what was the real number?
It's written, but I forget. I refer you to the sources. It's not a bad approximation. It's not a bad approximation. Also, there is difference between longest day and longest night. Longest day is not quite equal to longest night, but they ignore it. So there is a little bit. It's mentioned, but I didn't copy it. Okay, so latitude of moon in different. So longitude, I mentioned latitude of moon. Eclipse magnitude, this was measured in fingers, and so on. Daily motion of the moon, motion of the sun. So the sun is very interesting. For the sun, I mentioned in the abstract, for the velocity of the sun, they had 2 theories. So which I mentioned as system A and system B. And I mentioned in the abstract that system A is tersitu of Naburimannu and system B is tersitu of Kidinnu. What is tersitu? We don't know. There are several conjectures. One would think that maybe it means that it's discovery of Naburimannu, but this is in fact considered improbable by the experts. Maybe, we don't know precisely. So maybe it's the method, for example. So just system A, it has very simple, very good practical rule for computation of the velocity of the sun along the ecliptic. Very simple. So there are two equinoxes. Also, by the way, the positions of the equinoxes, they put axiomatically, dogmatically, in certain positions, areas 10 degrees. It's not very true. It's not very precise. It's really not very precise. It's more or less precise for the year 500 before Christ. It's really not particularly precise for those years from which we actually have the tenets. So it's one of these examples when we can only say we don't understand why this happened. Well, in any event, so they had these two equinoxes, and the velocity was simply taken to be constant along one arc and constant along the other arc, but one arc was considered a little bit faster than the other. It's very good. It gives quite reasonable conformity to what one observes. Quite sufficient for their purposes. The more complicated system B, instead of piecewise, so system A had four. So there is the ecliptic, there are the equinoctial. So the system, so here it's constant, and here it is slightly different constant. System B, you already guessed it. Instead of piecewise constant function, it puts zigzag function. This guy, zigzag function. So the speed increases a little bit and then decreases a little bit. It's quite clear that this is not what one observes. But it's good enough. It's good enough. It's good enough to make simple computations which give sufficiently good answers to practical questions. So length of months and this kind of thing. So it is clear, Van der Waalen writes, system A, the earlier one, the one with piecewise constant, with piecewise constant speeds. System A, which conjecturally is dated around 500 BC, and here I must apologize before my public, because so one thing one noticed very quickly in papers on Assyriology is that the experts very rarely agree with each other. So Van der Waalen writes something, and then Neugebauer writes that maybe one needs to be more skeptical and so on. Obviously, I don't read cuneiform, I'm not in a position to judge. So I have tried in this exposition to avoid all controversial issues. But notably, the issue of dating is where they agree that these systems, system A and system B, were probably, even though the tablets come from after Alexander, the systems were probably developed before Alexander, in the Achaemenid era. They agree, but Neugebauer doesn't agree with proof of Van der Waalen, because he points out that the proof of Van der Waalen, in fact, goes back to Kugler. One of the possible proofs is that precisely the position of the vernal equinox Aries 10, the position, but it's really false. It's really false. But it was sort of true for 500 years before Christ. Well, Neugebauer points out that this is really a very slippery slope. This is not a good argument at all, because observations of Babylonians were not particularly precise. But even a small mistake moves the date like 50 years. So the method of proof by saying that, well, the system was invented when this was the actual position of the vernal equinox is not very good, because even a small mistake moves the date by 100 years. Okay, here let me pursue a little digression. One of the major discoveries of the Greek astronomers was the precession of the equinox. So the equinox, since the rotational axis of the Earth wobbles somewhat, so the equinox every year is slightly earlier than the year before. Ptolemy in the Almagest gives 1 degree in 100 years. In fact, it's more like 1 degree in 72 years. So a natural question arises, did the Babylonians actually know this? So the only thing that Neugebauer has a special paper devoted to this subject, and he says that the only thing we can say that we don't know. The strange thing is that this vernal equinox is put in 10 degrees in Aries in system A and in 8 degrees in Aries in system B. And well, you might want to conclude, okay, this is because system B is later and they discovered the precession of the equinoxes. But in fact, no, because first of all, these are found in tablets used in the same time, and secondly, they do not evolve. So this is this strange paradox. Babylonians has this amazingly sharp mathematical machinery, but they use these data when they are quite clearly not true. They use these positions when it's quite clear that they are not true. So this is one of the enigmas of the story. How did this happen? One can only say that it is like this, but there is no clear explanation. And then there is another very important point, so I return from the digression to the main story. When we think about astronomy, even when we teach astronomy, when I was 6 years old and I went to the Moscow Planetarium, of course, what we do, what one explains, is what is called geometrical cinematical theories. So, this planet goes around this planet and so on, so there is this beautiful geometrical representation. This one rotates and so on. But there is absolutely no indication that Babylonians had anything like that. So it must be emphasized, the geometrical picture, even for example, the celestial sphere. The celestial sphere. Did the Babylonians have the celestial sphere? There is no evidence to this effect. The only things we have from Babylonian are numbers. We only have numbers. There is absolutely no geometric representation. So, for example, in the computation of these months' lengths, if I explain them in modern terms, so one can say that the Babylonians considered that the axis of the ellipse, of the Keplerian ellipse of, let's say, Jupiter, it was their favorite planet, is fixed. But we don't have any evidence that they actually had such notions, that they even discussed in such terminology. There is absolutely, it must be emphasized, there are only numbers. It's discrete mathematics. So there is no geometry, it's discrete mathematics. There are tablets of numbers, the sun rises, heliacal risings, so risings of Venus at sunrise, heliacal rises of Venus are recorded 1700 years before Christ. So, but there is no geometrical theory. There are just numbers and methods for manipulation of numbers. And again, since they had hundreds of years of observations, that even not very precise measurements, well, this should not surprise an ergodic theorist, even not very precise measurements give very good picture because the measurements were taken over a very long period of time. Okay, and then they had correction terms and so on. So, and now this much for the story. Now I want to again to say a few words about the influence of Babylonian astronomy on Greek astronomy. In fact, if one reads a classical textbook of astronomy, let's say from the beginning of 19th century, let's say Delambre, the French astronomer, he writes quite clearly, la seule astronomie que nous connaissons, c'est celle des Grecs. The only astronomy that we know is the Greek astronomy. So the Almagest was the main book in astronomy for 1500 years, before the work of Kepler. The work of Copernicus is still essentially very much influenced by Almagest. Its terminology is that of Almagest and so on. But just the really new discovery is the discovery of Kepler. But the really new astronomy is the astronomy of Kepler. But in any event, so Ptolemy is very conscientious with his sources. So in particular, the precession of the equinoxes. He ascribes this discovery to Hipparchus. And if he didn't, we wouldn't know that, we do know that Hipparchus existed, but we wouldn't know that hypothesis would work for astronomy in a serious way. So Ptolemy is very conscientious with his sources, and he mentions the Babylonian observations. The Babylonian observations. And so, in fact, he mentions that the Babylonian observations go back, I reformulate in modern terms, go back to 750 before Christ. This corresponds quite well to our actual data. Our data is roughly from this period. The tablets with observations with systematic observations, the tablets that we have are roughly from this period, so it's quite close to what Ptolemy says. But please allow me to emphasize. So he does emphasize Babylonian observations, but he gives absolutely no clue about Babylonian mathematics. This stuff, when the good Jesuit fathers discovered it, it was complete breakthrough. There is absolutely nothing in the classical sources to suggest this mathematical theory. So in parallel, in Alexandria and in Babylon, there existed very well developed geometrical astronomy, because, well, it's the one of the Almagest, but there is every reason to believe that Greek astronomy already, let's say, shortly after the death of Alexander, was in many ways similar to what is written in the Almagest. Ptolemy certainly perfected the work of his predecessors, but he certainly also built on a rich heritage. And, by the way, the first geometrical cinematical models go to Evdoxos, so at the time of Plato. So Evdoxos, so clearly, if one looks at the sky, one sees that the planet goes this way and then it goes back. So clearly this calls for explanation, retrogradation of some planet of Mercury, why it goes this way and then goes back, why? So already Evdoxos suggested the explanation with two concentric spheres. So there are two concentric spheres, in fact there are four, but the main role is played by two concentric spheres. So Aristotle mentions these concentric spheres of Evdoxos. So there are two concentric spheres. If there is a concentric sphere and the planet moves and then the sphere itself moves against another sphere, one can see retrogradations. And you can see that there are two complementary parts of the picture. The Greeks had a geometric picture, but which has no bearing on observational data. What you see from two concentric spheres has nothing to do with what you actually observe. In fact, conjecturally, the Greeks, when they came to Babylon, they must have been completely astonished by the fact that they had these hundreds of years of observation. Science in Greece was essentially a private undertaking. Well, there was the academy, but the academy was private. There was the Lyceum, but the Lyceum was private as well. In Babylon, it was in the temples. So it went for hundreds of years. We don't know exactly for how long. It went for hundreds of years. And when the Greeks, they came with Alexander, and Alexander resuscitated Babylon. So Babylon came back to prominence in the time of Alexander because the Achaemenids were not very prominent anymore. So he resuscitated Babylon. And they were amazed by this secular, centuries and centuries of experimental data. On the other hand, the Babylonians, they had this data which they manipulated with great brilliance, and they didn't have the geometric picture, or at least we don't have any evidence that they as much as thought so the sky was essentially a square, was essentially flat, and there were these planets moving along according to very clear rules, but without any, at least not that we know, without any effort to represent this geometrically. And in concluding, I would like again to emphasize the approximate and non-final nature of our knowledge. So, there are many things we know, let's say, about Alexander, and many things we don't know about Alexander. But it doesn't seem very probable that 50 years from now, our ideas about Alexander will be different from our ideas today. Certainly, our ideas 50 years ago and 100 years ago are not particularly different. There are some points are made more precise, but the main outline is the same. If you read a textbook on Alexander written 100 years ago, you pass the exam. So it's like, if you read a textbook on integral calculus written 100 years ago, it should be okay for an exam today. So it's completely different in the study of mathematics of Mesopotamia. So even though, not to mention astronomy, so with astronomy it's very simple. There is a cutoff. There is a cutoff. Earlier than roughly 700 years before Christ, there is zero, nothing. It doesn't mean that tomorrow something is not found. The society of Mesopotamia was very traditional. So, for example, the Epic of Gilgamesh, if you go to a bookshop and you buy Gilgamesh, it's a relatively, probably what you buy is a reworking from some 700 years before Christ. But the earliest versions of the Epic are over 2,000 years before Christ. So it is, to say the least, not impossible that, say, the Sumerians had some kind of astronomy. But there is zero evidence about this. What does develop slowly, and this is where the science is making progress as we're speaking, so is the early Sumerian mathematics. We are in position, maybe one can say, and it is being said that we are in position that the Renaissance was, so what, let's say, Dante knew about Greek literature is really completely not the same as what Tasso knew about Greek literature. There is no comparison. So we are roughly in the same position. So the new things are being discovered all the time, and specifically, so the mathematics, the very early Sumerian mathematics, because Neugebauer, he also put a certain cutoff on his research, and he did not discuss mathematics before 2,000 years before Christ. But it did exist. There is, by the way, a Russian researcher, Isaac Abramovich Weiman, who worked at the Hermitage and who did a lot of work on Sumerian mathematics before 2,000 years before Christ, when they didn't really even have, well, the writing system was still being very much developed, but already the positional sexagesimal positional notation for numbers was already in place. And the study of mathematical problems that they could solve, for example, a famous mathematical problem is that of reciprocals. So in sexagesimal notation, it is subtle to take reciprocals of numbers which are not powers of 60, like 1/7. But there exists a tablet, by the way from Cornell, a tablet which precisely computes 1/7, and so on. So which writes it in some way that it's possible to write 1/7. So I'm just trying to say that the picture that I'm making today, that I try to expose today based on the sources which we have today, maybe 20 years from now will be completely different. So it's Babylonian study of Babylon. It's not that we know little. One cannot say this. There are hundreds of thousands of tablets, maybe 500,000 tablets. But as I mentioned, it's local, very sharply localized in space and in time. In space and in time, because there are some specific sites and specific libraries from where one has the tablets, and the tablets that we have are in very sharply localized, describe some very specific spatio-temporal small parts. So we have these little dots of bright light in dark ambience, so like stars in the sky, and the research continues, and our knowledge on Babylon changes all the time, develops right now. In fact, as Arian writes about Alexander was never content with what he had already obtained, but he was always striving on the other side of the known, competing with no one but himself. Thank you very much.
But definitely they had this problem. As far as I understand, the tablets were in complete disorder.
Yes.
So it wasn't possible to place them in chronological order or something like that.
This is excellent question. Thank you so very much. Yes, it was because of simple function. Yes, it was because of simple function.
Yes. But
This is
I
excellent.
want to continue because
Yes.
I discussed this with our astronomers at our faculty. Now we have a possibility to, how to say, input all this into a computer and let the computer try to find some hidden order.
So to do
Because it's difficult for our mind, but such things are very natural for computers. Is that done?
So I read about this as work in progress, but I cannot comment. So clearly, Neugebauer and Kugler, but especially Neugebauer, certainly they did comparisons with modern observations. It's one of their riding horses, and in figures in the book of Neugebauer, there are all the time comparisons with modern. And by the way, the agreement is very good. The agreement is really very good. You can just open the book and see. And in fact, I read that they're using what's called deep learning for working with tablets, because is precisely, it seems like, the fashion of today. But this is all I can say. In fact, I read that this is an approach that is being tried.
I return, maybe I waste your time, but I return to astronomers, and their main idea was like that. We have a lot of observations for a long time when people studied the sky using telescopes, and even the first attempts to put this into computers gave new understanding of something like laws of.
But who did that? Who did that?
Sorry?
Who did that? Whose work is this?
I discussed it with Professor Ivanov, who is professor of astronomy.
But maybe it would be interesting to see what.
Faculty of Mathematics and Mechanics.
But has he published? Has he published his work?
Well, I don't know. It was private discussion.
Because let me explain. Because Neugebauer is very sharp exactly on this point. But again, how do I say? He is sharp about impossibility of something. So about negative conclusions. He is very clear that positive conclusions are very tentative. But precisely about Neugebauer emphasizes all the time that since many of these tablets precisely match, so it seems clear that it's not actual observations. So precisely, that's what the Greeks thought that these were, but these are not observations. These are sort of the tablets that we have. These are sort of calendars which are just periodically continued. So these are not new observational data. They had this is Neugebauer's reading. They had their, how to explain myself? They had their schemes, their mathematical theory, and then they just continued periodically. And this gave good agreement. Yes. So if Neugebauer is correct, then it would not be possible. Then it seems to me that what Neugebauer says contradicts what you say. But again, since more or less every two papers I opened contradict each other, this is not a new thing. So I think it's how do I say? It's really just it's a new field. It's a very young field. It's a very young field, and there is a lot to be done.
Is it something we know about astronomy of, say, Chinese?
It depends on who you mean by we. If you mean me, then no. But if you mean,
probably you write about history of astronomy.
This is the problem. Chinese, even mathematics. Well, there are some Western, very, very synthetic treatments, But I think the main texts are in Chinese. So, by the way, this is also true about Arabic science. It's not very easy to put your hand on mathematical works from the Arabic world. Many are not published at all, and many, if published, are published in Arabic. Some of them are published in Russian. So in Chinese, I think, if you don't speak Chinese, you will have trouble getting more than a very, very, very approximate idea. Indian astronomy, on the other hand, is widely believed to have been influenced, yes, by Babylonian astronomy, because precisely Alexander went all the way to India, and there is, well, at least if you look at the Indian system and compare it with the Babylonian system, again, putting it roughly, it seems more or less like the same thing, and it seems reasonable that in the Hellenistic world of Alexander, knowledge traveled. So Indian astronomy is quite similar to Babylonian, or at least, how shall I say, a good case can be made for borrowing from Babylonian astronomy. But Chinese, I really have nothing to say.
500 BC, right?
No, excuse me, maybe I wasn't very clear. So, conjecturally, these mathematicians, Naburimannu and Kidinnu, by the way, they are mentioned in Greek sources. They are mentioned by Strabo in geography, just by name. So, conjecturally, the method was discovered. There are several proofs for this. Were discovered roughly 500 or maybe 450 before Christ. But the actual evidence, we have the actual tablets, which Kugler and Neugebauer and so on will work with, are much, much later. In fact, in Neugebauer there is a graph of tablets, of number of tablets by time, and there is a sharp peak after Alexander. Why? Your guess is as good as mine. Why? But we don't have it. So this thing about it being from Achaemenid period is theoretical reconstruction. It's not based on actual evidence. Our evidence is all from Seleucid period.
The following: the ancient Egyptian civilization existed much before that.
That's so
true.
That's so true.
So they were doing observation probably because they needed to predict many things.
No. First of all, Egyptian civilization and Mesopotamian civilization, there is no significant difference of age between the two.
Well, it's at least 2000 BC. They had.
Yeah, 2000 BC is already Babylon, but they were at least 1,000 years before that. The Sumerian time.
Yes, no.
So precisely. So there is no.
So there's a gap like 1,000 years when people were making observations.
But that's precisely what I was trying to point out, that there are gaps in our knowledge.
It's a gap of our knowledge, or just it was nothing?
Based on what do you want me to answer this question?
No.
If we have no evidence.
No. It looks like you read a lot of literature and stuff. So
Yes, no, but we don't know. No, but excuse me, if there are no sources, how can you... No, okay, let's put it this way. So for mathematics, we know, because we have mathematics from Old Babylon, roughly 1800 before Christ, 1800 before Christ, and in fact quite late mathematics, so 1,000 years later. And in first approximation there is no difference. It's more or less the same problems and solutions, same thing. But for astronomy we just don't have any. We have a little bit. There are so-called tablets of Amitsaduga. These are tablets from Old Babylon with heliacal risings of the moon. But it's like one set of tablets, as opposed to 1,500 tablets from Seleucid era. We don't know. We don't have evidence. So making conjectures without evidence is very slippery, precisely, by the way, because here there are many false conjectures. So in this, what I explained is, well, the answer as of today, but there were many intermediate conjectures which were then proven false. So it's not.
The reason I'm asking about the Egyptians because we have thousands of kind of inscriptions left by Egyptians from earlier period,
But not astronomical. Egyptians, in first approximation, Egyptians didn't have astronomy. There is no comparison.
So that's exactly my question.
Okay, so now I think it's how to say, you can conjecture. So one can. Okay, let me give you a different example. If there is some discovery which Byzantinians had and Arabs had, if you read a Byzantinist, he will tell you that it's the Byzantinians who did it. If you read an Arabist, he'll tell you that the Arabs did it. So I don't think tracing influence of Babylon on Egypt, it is reasonable to assume that influence existed. But such a conjecture is much more easily formulated than proven. So, it seems fairly clear that in Ptolemaic Alexandria, of course, there was some influence. Well, this seems fairly clear, precisely because Ptolemy wrote the Almagest, and he mentions, but we don't have any earlier. So we have mention of Chaldaean astronomers. We have mention of them, but we don't have any mention of the mathematics or astronomy they did. We only have some mentions of them. Let me give you another example. Thales, the one of the Thales theorem, famously predicted an eclipse. How did he do it? So Van der Waalen says that clearly it's because he was influenced by Babylonians, and Neugebauer says that it's clearly because he was not influenced by Babylonians.
Maybe he was lucky.
Well, no, then he knew. No, predicting an eclipse, lunar eclipses. It was lunar eclipses. Lunar eclipses take place reasonably often. So maybe he had, So I think in Ptolemaic time it's reasonable, quite reasonable to assume influence of Babylonians on Egyptians, and in earlier time I think it's, how do I say, it takes much more conjectural courage. Yes?
You said about angular velocity of the sun, that it isn't constant.
No, it's not.
We're speaking about angular velocity with respect to fixed stars. And it's important to understand why isn't it constant. In fact, because the orbit of Earth is not a perfect circle with sun in the center, or speaking in another way, the distance between Earth and sun is variable. There is a perihelion where the velocity, relative velocity of Earth to the sun is maximal and angular too, and there is aphelion where there is minimal angular velocity.
But I completely agree with you. I'm just pointing out that the Babylonians, as far as we know, did not as much as reason in such terms.
They didn't understand reasons, but questions. I will explain my point. It's important to understand that positions of perihelion and aphelion are irrelevant to equinoxes. On the scale of human civilizations, the orbit of Earth is nearly constant. This position don't change. And if in Babylonian time there has been some coincidence with such points which are used to approximate the velocity of the sun with equinoxes and solstices, then it was a coincidence of their epoch. And when you discuss why didn't these systems evolve from systems A and system B, it's important to specify which references do you use.
You speak like Neugebauer, I completely agree.
If you use fixed stars, then the orbit of Earth, or the relative orbit of Earth and Sun, shouldn't change.
But we completely agree. We completely agree. I think there was another question here. Or maybe. Yes.
Maybe my question is not so closely connected, but you mentioned that in Hellenistic time,
Yes.
it was some difference between maybe astronomy in the ancient Greece and in Alexander time. Yes.
Yes, very much. Yes, of course. Yes, very clearly. Yes.
An opinion that there is some crisis in culture, in Greek culture in Hellenistic time. What about the science? What do you
No,
think?
but the time of Ptolemaic Alexandria is an explosion of Greek. Is the one of the highest points of Greek culture. So Ptolemy Soter was friend of Alexander, and you must understand his situation. He had a big kingdom with many subjects, of which only a tiny minority were Greeks. These people prayed to different gods. They spoke different languages. They had different religions. In particular, there were these Jews who had this god, and nobody could understand what they actually believed. So he had this kingdom to unite. So how do you unite it? What is universal? Universal is science. So that's why he builds museum and library. And in the library he orders a translation of the Jewish books, the famous translation of the 70. So this is, it was explosion of Greek science. So there was Euclid, Eratosthenes, the astronomers, they were maybe not in Alexandria, but for example Achaemenids, he did not really live in Alexandria, but he corresponded with Eratosthenes, so they kept contact. They kept contact with Alexandria. No, it was just the age of gold. In fact, it said age of gold. Then there was the poets, Callimachos. It was unbelievable age of gold for Greek culture. So, because Greek culture suddenly became global. After Alexander, the world spoke Greek. So it became the culture of the world. So, and I jump ahead a little bit. Famously, there was famous translation movement in Arabic world when they translated the Greek books. In fact, translation movement starts in Persia, before the Arabs, in Sassanid Persia. How did they explain this? How did the Persians explain why we translate Greek books? They said, when Alexander came, he translated our sacred books to Greek. And now we are just taking back our own. So in fact, it's our wisdom. He just translated it. The Greeks, they came and they took it from us. And they translated it. And now we are taking, this was the explanation. It's written, this is the explanation. So, but it's going back to Alexandria. Alexandria was the cultural capital of the world. So it's far from a decline. It was just the golden age. Very short-lived. But it was just golden age, absolutely. So you can, even today, every textbook of geometry, give me any textbook of geometry of today, the author is in dialogue with Euclid. Maybe like Alexandrov, he follows Euclid. Maybe like Kolmogorov, he polemicizes with Euclid. But just take any geometrical textbook of today and put it side by side with Euclid elements. You will see that these books are interdependent. So we live in the world of Alexandria even today.